So let us begin our today's session on basis and dimension. So this class is the repetition of 30th October. So we are going to cover the same topics of that class and some other concepts with regarding to basis and dimension, right? So please take a note of that. So let us start with basis. Now, before that, whenever we consider a vector space V of F, suppose this is a vector space, say V of F. In this vector space, let us take a set of vectors, say alpha 1, alpha 2, so on, alpha n. We say that this is a spanning set for V of F if every element in V can be written as a linear combination of this spanning set. In other words, whenever you take a vector gamma belongs to V of F, then you can write gamma as A1 alpha 1 plus A2 alpha 2 plus so on plus An alpha n. Then we say that the set alpha 1, alpha 2, so on alpha n spans V. If this set is also linearly independent, then we say that it is a basis for V. So what is the definition of basis? Whenever we take a vector space, in that we are considering a set of vectors which spans V and it is also a linearly independent set. So the set is having two properties: one, linear independence; second, spanning the whole space. Such type of sets we call them as basis for the vector space. So from this we arrive at a definition that what is meant by a finite dimensional vector space. Whenever we consider a vector space, we call it as finite dimensional if it has a finite spanning set. That means you are able to find a set having finite number of elements in V such that whatever the vector you take in that will be written as a linear combination of those vectors. And there is one good result that whenever you have a finite dimensional vector space, it always has a basis. In other words, every finite dimensional vector space contains a basis. So from this, the definition can also be termed as finite dimensional vector space is nothing but having finite basis. So obviously a vector space may have so many bases. That means in a vector space you can find so many sets such that which satisfies the two conditions. One is spanning set, another one is linear independence. So whatever the basis you consider, always the elements may differ, but the number of elements are fixed. The number of elements are fixed. So the number of elements in any basis, we call it as dimension. The number of elements in any basis, we call it as dimension. Okay, so please take a note of that. Now the question is, how to find a basis? For this, there is one small result, that if you take a vector space V of f and consider a linearly independent set in it, then either it becomes a basis or it can be extended to form a basis. So whenever you consider a vector space, if you take a linearly independent subset in it, then it will become a basis or it can be extended to form a basis. This result is known as basis extension theorem. And if you talk of the geometrical significance of the basis, suppose you take the vector space R cube over the real numbers. As we know, for every finite dimensional space, we will have a basis. For this, the default basis is nothing but the combination of ones and zeros. So it is nothing but 1 0 0, 0 1 0 and 0 0 1. Apart from this, you will get different bases for R cube. So if you visualize this geometrically, it is nothing but x-axis, y-axis and z-axis. Because whatever the 3D vector you consider in it, that is nothing but first vector 1 0 0 x-axis, second vector 0 1 0 y-axis and third vector 0 0 1 z-axis. So every 3D point can be represented in terms of x, y, z axis. So that is a standard basis for R cube. Not only for R cube, for R square, R power 4, so on. For everything, the combination of ones and zeros will give the standard basis for it, because it is linearly independent and it spans. And if you take any other basis, for example, say 1 1 1, 1 1 0, say 2 3 1, then if we say that this is a basis, it defines a new coordinate system. First vector, second vector, third vector. So it acts as a new coordinate system in the 3D space, so that every 3D point in R cube can be represented using a combination of that axis. So for geometrical purpose, for R square and R cube, you can view basis as the coordinate system. If the elements are polynomials, matrices, etc., etc., then if you talk of basis as geometrically, it is not possible to visualize them. So you just imagine that it is the largest linearly independent set in the vector space. So its significance is nothing but the largest linearly independent set in vector space. So if you take a set having more number of vectors than basis, obviously it becomes linearly dependent. So let me say, if I have said that dimension of the vector space is equal to 10, it means that you can find a linearly independent set in V having 10 elements. And this is the largest linearly independent set. That means the largest magnitude of the linearly independent set in V is nothing but 10. So if you take any set having more than 10 elements, it becomes LD. So if I take any set more number of elements than this, it becomes LD. That is the significance of basis. As we know, the number of elements in any basis is called dimension. So here the dimension of the vector space is 10. So you can find a basis for V with 10 elements. That's it. Now let us take some sample problems over this concept, how to find it. The usual procedure is, suppose if you say V of f is a vector space and say alpha, beta, gamma is a basis in V. So you should prove that the set spans the given vector space and it is linearly independent. So the first step you need to do is, you should write a linear combination using those vectors, and we should prove that the scalars are 0. And second one, for spanning, you take any vector in V and write a linear combination using the given vector set. Now you need to find an expression for the scalars PQR such that PQR have an expression in terms of the coordinates of this. Let me say, suppose if we are having R cube as vector space, then X is nothing but a 3D point XYZ. So whenever you take any arbitrary 3D point, if you consider a linear combination, then you are going to find an expression for the scalars PQR in terms of XYZ. So you are representing the scalar P in terms of XYZ, similarly Q in terms of XYZ and R in terms of XYZ. So this is the general way in checking whether a given set is a basis or not. Suppose if the basis elements are nothing but simply points, suppose if you are dealing with a 3D space R cube, so you will get 3 vectors, let me say 1, 2, 3, 2, 1, 1 and 1, 1, 0. So if you want to check this set is a basis or not, so for linear independence you simply calculate the determinant. If the determinant is not equal to 0, then it is linearly independent. If the determinant is 0, then it is linearly dependent. So this technique is applicable whenever you get a matrix form. Otherwise, we always stick to the definition that writing linear combination, proving that scalars are 0, writing linear combination and proving that the scalars has an expression in terms of x, y, z. That is the usual way. Okay. So for every problem, we do the same procedure. So now let us take one of the previous year questions. Let us do some problems. The first one is find dimension and basis for general solution of homogeneous system So this is the given system of equations. So here we need to understand that the solution satisfying the three equations, the homogeneous system of equations, is nothing but a vector space. So for that vector space, we are finding a basis, and if you count how many elements are there, that gives the dimension of the vector space. So as we know how to solve the homogeneous system, let us write the corresponding matrix form here. So you will get that 1, 2, minus 3, 2, minus 4, 2, 4, minus 5, 1, minus 6, then 5, 10, minus 13, 4, minus 16. Now let us reduce that into echelon form. We apply the same row operations as usual. So R2 tends to R2 minus 2R1 and R3 tends to R3 minus 5R1. Then again we apply the form that R3 tends to R3 minus 2R2. Then it will be equivalent to the form as so from this, if you observe that the rank of the matrix is 2, you can check for the row operations, that would be the possible result. So as usual, since the rank is 2, how many independent solutions will be there? Number of independent solutions is equals to number of variables minus rank, that is equal to 3 solutions, because we have 5 variables and the rank of the matrix is 2. So you will get 3 solutions. Generally, whenever we consider the variable matrix x1, x2, x3, x4, x5, we take that the last 3 variables are constants. Say this is K1, this is K2, this is K3. So if you take the respective constants there, then from the second equation you are going to get x2, and substitute in the 4 values in the first row, you will get x1. But here what happens, If you take that the last three variables are constants, since the position of x2 is 0 here, you cannot find x2. That's why we take the constants as x2 is equal to a constant, then x4 is equal to b, a constant, and x5 is equal to c, a constant. So substituting the values here, you will get x3 and you will get x1 also. So this is the difference between regular homogeneous system of equations and this problem. If this position is a non-zero one, then by default we take that this is a constant, this is a constant, and this is a constant. Since this makes 0, it has a difference, so we fix that x2 is a constant, last two variables x4 and x5 are constants, and x3 will be determined. Since you know how to substitute the values and determine the equations, I will give the respective solutions. So substituting the values there, you will get the respective vectors as the first vector will be and for the second one, and for third one it is so these three vectors together constitute a basis for the solution space. The set of all solutions for that homogeneous system is nothing but a vector space, and for that vector space these three vectors becomes a basis. Since the number is 3, the dimension of the vector space is nothing but 3. That was the conclusion of the problem. So if you have any other queries, you can ask. Please tell. And please take a note of it, then I will take the further problems. Now, while proving the problems of linear independence, let us take one interesting problem that you take the set as F, G and H, and you are going to check whether this set is linearly independent or not. And the elements in the set are given by F is nothing but sin t, G is nothing but cos t, and H is nothing but e power t. You take like that. Or you can simply take it as t also, where each one is a function from R to R. F, G and H, each one is a function from R to R. So here what happens, generally to check for the linear independence, we will write the linear combination. So please understand that the 0 on the RHS indicates the 0 function, and A, B, C are nothing but the scalars taken in the field. Now what happens, let us substitute the values. So if you are able to prove that the values of the scalars A, B, C are 0, then the set is linearly independent. If you can find some non-zero values for A, B, C, then it is linearly dependent. Here we need to understand that in that linear combination we have considered the result as 0 for all values of t in R, because the functions are defined from R to R. So you are assuming here that whatever the value you take for t, the result is 0. So in order to prove ABC, we should get a homogeneous system of equations in terms of ABC. For that, I will substitute different values for t. So I can take t is equal to 0, I can take t is equal to pi by 2, I can take t is equal to pi, I can take t is equal to 2 pi, etc., etc. So if you substitute the respective values there in this equation, if you substitute t is equal to 0, you can say b is equal to 0. So if you substitute t is equal to pi by 2, then you have so from this you can say that a plus c into pi by t equal to 0. If you substitute t is equal to pi, then the result is so from this you have an equation and also you have another equation that since b is 0, substituting b value here, you will get c is equal to 0. Since c is 0, you will get a is equal to 0. Therefore, a, b and c, all the three values are 0. Therefore, the given set X is linearly independent. Please understand that the values of t what I have considered are at our will. You can take 0, pi by 2, 45 degrees, 2 pi, 3 pi by 2, anything you can take. The only thing is, by substituting different values of t there, you will get a homogeneous system of equations. From that you should be able to deduce the values of ABC. Either they may be 0 or they may be non-zero. Depending upon ABC values, we will confirm that the set is linearly independent or dependent. That is one way. Okay. So please take a note of that. Then I will take the other model. Right. Now, if you take a vector space V of f and say W1 and W2 are subspaces in V. Then obviously the intersection and the sum are also subspaces of V. So if you want to determine their dimension, there is one small result that so dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So based on this formula, let us do one small problem which is interesting. So please take a note of that formula. So here the vector space is taken as R power 4 and the subspaces are taken as W1 is equal to set of all ABCD such that b minus 2c plus d equal to 0, and wt is equal to set of all a, b, c, d such that a equal to d and b is equal to 2c. So from the very definition of subspaces, we need to understand that W1 is nothing but set of all 4D points in R power 4 such that if you observe the coordinates B, C, D, they satisfy this equation. Wt is nothing but set of all 4D points in R power 4 such that for the coordinates they satisfy this one. So first and fourth coordinates are equal and second coordinate is twice of the third coordinate. So you are going to find the respective dimensions and the dimension of the intersection. That was the task of this problem. So if you consider W1, if you take any value A, B, C, D. So here from this equation you can say that B is equal to 2C minus D. So you can write this as A, 2C minus D, C and D. So what happened? I replaced the coordinate B with the respective value 2C minus D. So if you write it as a linear combination, it will come like this. Here the linear combination is obtained as by simply taking the coefficients of the variables. I have simply written the coefficients of A, C, D in the respective positions. First position, second position, third position, fourth position. Now what happens? The three vectors 1, 0, 0, 0, 0, 2, 1, 0 and 0, minus 1, 0, 1 together constitute a basis for W1. Since they are 3 in number, dimension of W1 is nothing but 3. Now let us do the same procedure for the second set W2 and what is the basis for it. So if you consider any value in W2, whatever the 4D vector ABCD you take, from its point of view it is nothing but A is equal to D and B is equal to 2C. A is equal to D, so I have replaced A with the value D. B is equal to 2C, so I have replaced B with the value 2C. So if you take the respective variables as common, it will come like this. So if you observe that the two vectors 0, 2, 1, 0 and 1, 0, 0, 1 together form a basis for W2. Hence, dimension of W2 is nothing but 2. Now, let us find what is the dimension for the intersection. So let us go for it. So we are going to find the dimension of the intersection here. So if you consider the intersection, so intersection is nothing but whatever the value ABCD you take in the intersection, it satisfies the first condition as well as the second conditions. So from this you can say that so you have A is equal to D, B is equal to 2C and B minus 2C plus D equal to 0, which is nothing but B is equal to 2C minus D. So if you substitute this value here, you have 2c minus d is equal to 2c. So from this you can say d is equal to 0. Since d is equal to 0, a and d are equal, you can say that a is equal to 0. So it will come as 0, b is equal to 2c, c and 0. So if you take the respective variable as common, so the single vector 0, 2, 1, 0 will become a basis for the intersection. Therefore, the dimension of the intersection is nothing but 1. So if you simplify that, dimension of W1 plus W2 is nothing but 4. So dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of the intersection. So please take a note of that. So in this way we solve the problems by simply finding the linear combination using the given condition, right? So if you are clear, I will take the other model. Now, the next thing is, usually while finding a basis, generally we start with a spanning set. Obviously, we write it as in the form of a matrix. And we apply row operations on it. Then you will get a new matrix. Now what happens, in order to get a basis, after reducing it into echelon form, you will get new vectors there, and we are saying that the new vectors are a basis. Now what happens, if you want to find a basis using the same given vectors, so if you want to find a basis using same given vectors, so what is the procedure for it, right? So let us take a small problem in order to find a basis using the given vectors. Now let us take the problem that I have taken the vectors u1 is equal to 1, 2, minus 1, 3, 4, and u2 is equal to 2, 4, minus 2, 6, 8, and u3 is equal to 1, 3, 2, 2, 6, and u4 equals to 1, 4, 5, 1, 8, and u5 is equal to 2, 7, 3, 3, 9. Suppose I want to determine a basis using the same vectors here. So by default we assume that the given vectors are nothing but the spanning set. So you are finding the basis for a subspace spanned by these 5 vectors. We need to understand like that. So here the 5 vectors are spanning set for a subspace in R power 5, because if you want to determine a basis for R power 5, you simply write them in the form of a matrix, the 5 vectors. You calculate the determinant. If it is not equal to 0, therefore it is Li, and by default the given set is nothing but a spanning set, so it becomes a basis. Here the thing is, the 5 vectors which are given there in the problem are a spanning set for a subspace in R power 5. So here you need to understand this is R power 5, and here you have considered a subspace, say W. For this W, this is the spanning set. So if you terminate the dependent vectors in the 5, then you left with the independent vectors, which is nothing but the basis for W. So in order to get a basis using the given vectors only, not of different vectors, so we simply write them in the form of a matrix. And here the vectors are written as columns in the matrix. So first vector is written like this. Now what happens? We simply apply row operations on it. Now please understand that this procedure we call it as casting algorithm. So for our convenience, let us simply understand that it is the echelon form model. The only thing is, usually we write vectors as rows. Here we write the vectors as columns. So you simply apply the row operations on it as this, and after reducing that into echelon form, we will calculate for the rows. So this will be equivalent to, after applying the row operations, it will become like this. So in this, we understand that while moving from left to right, which columns have same pattern? So if you observe that the first column, only the first value is non-zero, remaining are zeros. So while checking for the other columns, we check that for what columns the first value is non-zero and the remaining values are completely zero. So those columns are completely dependent on the first column. So they will be reducible and they can be made to become zero. So we consider the first column as fixed. Remaining such columns we won't take into consideration. So if you observe that the second column is dependent on the first column, so we don't consider that. Similarly, if you move from left to right, the next column is left as the third one, 1, 1. Here the first two positions are non-zero, remaining are 0. Again we checked for the similar pattern. What are the columns where the first two values are non-zero and the remaining values are 0? So if you observe that fourth column will be of the same pattern, so we remove that, we consider this column. And again, since the last column is left, which is different from this one, we consider as it is. So what happens? The basis is nothing but U1, U3 and U5. If at all, if you want to fix U4, U3 will be removed, you can consider U4. So in this way, we can find a basis obtained from the given vectors only. So here you are not finding a different basis. In the given set of vectors, you are eliminating which are dependent, and we are considering only independent vectors in that. So this is one good model. So please take a note of that. So if you have any queries, you can ask. So if you are clear, I will take the other models. Please understand that third and fourth are similar, accepted? The same pattern. So you can find the basis as U1, U3, U5, or this is also a basis and this is also a basis. Because a vector space may have so many bases. So among that, you are fixing what are independent columns and what are dependent columns. You are picking them. So this is one kind of basis, this is the other kind of basis. Since you are moving one after the other, what is the next different pattern? So third column has different pattern, and you are checking the pattern of third column with the remaining columns. What are the remaining columns? 4, 5, 6, 7, etc., which are identical pattern with third column. That's it. Those identical patterns are removed and you are fixing one column. So if you start with fourth column, that is also acceptable. So either this is a basis or this is a basis. Here the pattern is, see, if you take first column, only first element is non-zero, remaining are zeros, right? So you are also checking from second column to last column, what columns have same similarity. First value is non-zero, remaining are completely zero. That is what you are checking. Pattern means. Okay? Now you got the point. So this is a basis or this is a basis as per the patterns considered. Accepted? That's it. Any other questions, please? Fine. Let us go for one definition, that direct sum. What is meant by direct sum? So whenever we take a vector space, you are partitioning the vector space into a unique way. So that thing we are calling it as direct sum. So if you want the definition of direct sum is, whenever you take two subspaces for V, we say that V is direct sum of W1 and W2 if V is nothing but the sum and the intersection of the two sets is 0. The actual definition is, every element in V, say alpha, can be written as alpha is equal to x plus y, where x belongs to W1 and y belongs to W2 uniquely. So every element in the vector space can be written as sum of two values in the unique manner. So if, in other words, you can split the value into sum of two values in only one representation. 2 or 3 representations are not available for that, for the splitting. Such type of thing we call it as direct sum. For this we simply say that V is equal to W1 plus W2. That means every element in V can be written as sum of two values, and the intersection of the two sets is nothing but 0. So symbolically we write it as V equal to W1 plus W2. This symbol indicates the direct sum. You can extend this concept to any number of subspaces, W1, W2, W3, W4, so on, Wn. But generally we do the problems with two sets. That was the thing. Now if you want a small example, suppose you have considered all the square matrices of order n. Over the real number system. Say this is the vector space V. Now what happens? You consider W1 as all n by n square matrices such that who are symmetric, and you consider W2 as all n by n square matrices which are skew symmetric. Then it is possible to write V as direct sum of these two, because let us say I have considered a matrix A belongs to V. Now I can write this matrix as A is equal to sum of two values, where the first matrix belongs to W1 and second matrix belongs to W2. How is it possible? You can write it as A is equal to A plus A transpose by 2 plus A minus A transpose by 2. If you check that, the first one is symmetric, the second one is skew symmetric. As you know, every square matrix can be represented as a sum of symmetric and skew symmetric matrices. So the first matrix belongs to W1 and the second matrix belongs to W2. So here the first condition is satisfied that V is equal to sum of two values. The second thing is we should prove the intersection of the two sets is simply 0. That means you cannot find a non-zero matrix which is common to both W1 and W2. How to prove that? For example, let us say I have taken a matrix in the intersection. So here B belongs to W1 and B belongs to W2. This implies that W1 contains symmetric matrices. You can say that B is equal to B transpose. Since W2 contains skew symmetric matrices, you can say that B is equal to minus B transpose, or B transpose is equal to minus B. So from this, observing the two patterns, you can say B is equal to minus B, because here you got B transpose is equal to B, here you got B transpose is equal to minus B. So which gives that 2B is equal to 0 matrix, implies that B is a 0 matrix. So whatever the matrix you are taking in the intersection, it is becoming 0. Therefore, the intersection is nothing but singleton 0. That means only 0 matrix is presented in the intersection. You cannot find a non-zero matrix for the sets. Therefore, V satisfies the two conditions, so V is the direct sum of the two subspaces. So you please take a note of that. The thing is, you should be able to say that every element in V can be represented as sum of two values, and the second one is, you can say that the intersection of the two subspaces is 0. That's it. So I want to just take one small example over this. Which also gives you a good idea. So can I erase this? Suppose if you consider the vector space is equal to R cube, the three-dimensional one, then what happens if you take one vector space as xy plane and the second vector space as yz plane. So the symbolic representation for them is nothing but it is of the form all 3D points of this form. It contains all 3D points of this form. Now I will say that here the vector space V is not a direct sum of W1 and W2. Why? Because if you take the vector 3, 5, 7, then you can write it as in two ways. And the other way is nothing but now you can observe that for the vector 3, 5, 7 which belongs to R cube, it has two representations. Therefore, it is not a direct sum. So, if you observe the pattern of this, so here you have a common thing here. So, as and when there is a common thing, you have the intersection is not equal to 0, because the intersection of xy plane and yz plane is nothing but y axis. So, whenever the intersection is non-zero, obviously it is not at all a direct sum. That we should keep into mind. So let us take some other models. Now, as we are writing the linear combination is not only applicable to the vectors and it is also applicable for the matrices also. Suppose you take a matrix M is equal to 4, 7, 7 and 9, and you take the matrices as A is equal to 1, 1, 1, 1 and B is equal to 1, 2, 3, 4 and C is equal to 1, 1, 4, 5. Suppose I want to write M as a linear combination of these three matrices. So it is simply nothing but M is equal to x into A plus y into B plus z into C. So I need to find what are x, y, z. So what are the scalar values of x, y, z that I want to find? So if you simply substitute the values there, so you will get it as x into 1, 1, 1, 1 plus y into 1, 2, 3, 4 plus z into 1, 1, 4, 5. So you will get a corresponding system here, which is nothing but x plus y plus z So if you equate them, you will get a corresponding system of non-homogeneous equations. Now, if you solve this system by any method using row operations or Gauss elimination method, whatever the thing, if you are able to find the values of x, y, z, then you are done. So I will say that if you solve this system, you will get x is equal to 2 and y is equal to 3 and z is equal to -1. So m is nothing but (2a plus 3b minus c). So in this way we will find a linear combination. So this part is applicable for whatever the elements you take. You can take matrices, polynomials, functions, points, whatever the thing you consider. Linear combination is nothing but simply you are determining the scalars taken in that field. That is most important. Is that clear? Say. Right. Now, here I want to say one small thing, that whenever you are finding a linear combination by means of a basis, whenever we find a linear combination by means of a basis, then the scalars in that are called coordinates. So whenever we find a linear combination and the values used in that linear combination are nothing but basis vectors, then the scalars in that linear combination we call them as coordinates. Please understand that coordinates will vary from basis to basis. Since a vector space may have so many bases, you cannot fix the coordinates. If you use standard basis, you will get one type of scalars. If you get another basis, you will get another kind of scalars. So please understand that coordinates are purely based on basis. That's it. Okay. So if you are clear, then let us wind up our session here. I think I have taken all the possible topics of that 30th October session. So if you want to say something, you can add here. So in the end, I just want to take one small definition, then we can wind up the session. That is coset. So what is meant by a coset? Suppose you take a vector space V of f and a subspace W. Now, coset means if you take any vector in V, alpha plus W or W plus alpha, we call it as a coset. And how it is defined? It is defined as that means for every element in W, you are adding alpha. So if you want a geometrical view, suppose you consider the R square as vector space, the two-dimensional thing. Now what happens? Subspace is nothing but any line passing through the origin. So simply y is equal to mx is a subspace. So alpha belongs to means you fix a point. Any point you can fix in this thing. Now W plus alpha is nothing but another line parallel to it. So this is called as coset. So how many cosets will come? So how many vectors are there in the vector space? That much number of cosets you come. Now what happens? You will have distinct cosets and you will have repeated cosets. On the whole, that is the geometric view with respect to a coset. Now based on this, if you consider all distinct cosets, as a set, it becomes a vector space. We call it as quotient space. So it is denoted by with the symbol V by W. So what is meant by quotient space? V is a vector space, W is a subspace, V by W is called quotient space, and it is nothing but set of all cosets. And how the operations are defined on it? So whenever you take two cosets, the sum is defined as, and the scalar multiplication is defined like this. So using these two operations, it will become a vector space. So the first operation is nothing but coset addition. The second operation is nothing but scalar multiplication of the coset. So if you consider all the cosets together into a set, it becomes a vector space with regard to these two operations, and we are calling it as a quotient space. Now what happens? For every vector space, we are finding the dimension. So if you want a dimension and a basis for it, the formula is dimension of V by W is equal to dimension of V minus dimension of W. This is the formula used to find the dimension of the quotient space. However, questions were not yet framed on this concept, but the formula is useful whenever a problem is asked on this concept, right? So that's all for today. If you have any other questions, you can ask. Or we will meet in the next session with a new start with regard to solid geometry. So in the meanwhile, I will request everyone to solve the previous year questions. I will give the respective sessions with regard to typical problems. I think majority of the questions or models are covered with regard to previous year papers. You are able to solve each and every model. So we will start with solid geometry, right? Thanks.